So, good afternoon. Today we're going to continue looking at basic elements of Python, and we're going to look at comparisons, so relational operators, these Boolean values which are true or false, and how we can use this for conditional execution. The if statement allows us to write our code in a way that it can respond differently to different circumstances depending on how some conditions are evaluated. So we're going to see how to use that to create branches in the execution of our code and have it respond differently to different conditions. Then we're going to look also at namespaces and how we can import objects from other modules into our own modules. So a Python module is one file where you have the source code, that .py file that we have been saving, but we also have lots of other modules that are provided by libraries we have installed, by other code that we may have written, and we're going to see how we can bring together objects, for example functions, classes and so on, from different modules. So basically to reuse code. And we're going to use that to use data from remote resources. So in particular, in the example I'm going to give, we're going to use data from Wikipedia that we can download and process locally. So first, let's look at these operators. These are operators that allow us to compare values. So to ask if they are equal, different, greater, smaller, and so on. And they return one of these two values, so either true or false. These are actually objects, part of the built-in set of objects that Python has. So when you have a false comparison, for example, 1 equals 2, note that to ask if 1 equals 2, so this comparison operator, you use 2 equals sign. The reason for that is that 1 equals sign is the assignment operator, and that would be a syntax error in this case because you need a variable here to assign a value to it. So if you want to check if two values are equal, you use 2 equal signs. In this case it's false. Different is not equal, so you use the exclamation point there before the equal, and in this case it's true. 2 is not greater or equal to 5, so this is false, this is true, and so on. This also can be applied to sets, for example to strings, to lists, tuples, whatever. These are compared in order, and the comparison will compare each element at a time and then reach a conclusion about which of the sets are smaller or larger. For example, in strings it uses alphabetical order, so the C is less than D. For lists it's going to compare object by object, but in this case this list has fewer objects than that one, so this one will end up being less than that one, and so forth. So depending on the sets, if you have questions about specific situations, different sizes, different ordering and so on, you can either look up the documentation or experiment, but this is something that it's less often used in general, except perhaps for sorting strings. So for other sets things may be a bit more complicated and you should check if things work as you intend. You can also join a series of chain together a series of relational operators, and the meaning of this is a conjunction. So this is true because 1 is less than 4 and 4 is less than 6. So in this case 1 is less than 4 and 4 is greater than 2, so you can put them together like this, and this makes it easier to determine, for example, if one value is between two other values and things like that. These comparisons only work for compatible types. So in some cases Python does the conversion implicitly. For example, if you are comparing a floating point number to an integer, Python can do that and immediately converts and realizes that 10.0 is 10, even though these are different types of values. So this is an integer, this is a floating point number, but Python can tell that this is true, they are equal. In most cases, you need to do your own conversion if you're trying to compare different types of objects. For example, comparing the integer 10 to the string 10, Python will tell you that this is not supported between these different types of objects, integer and string. So you have to actually do your own conversion if you want to do the comparison. In this case, converting the string into an integer representation and then comparing. You can also combine these Boolean expressions, so everything that can be evaluated as true or false can be combined with these operators: negation, disjunction, and conjunction. So negation inverts the truth values. This is true, 1 is greater than 0, not this becomes false. And is a conjunction. It's true if both operands are true, and disjunction is true if at least one is true. So in this case, this expression here is false because first priority is the not, so not negates this comparison. So since this would be true, this becomes false, and now we have true and false, which is false. There are other examples here. So basically, with the disjunction, you need only one of them to be true. So in this case, this one is true. So even though this one is false, the result is true. With the conjunction, you would need both of them to be true. So in this case, it's false. You can use parentheses if you want to create more complex expressions, but remember the priority ordering. So first, Python evaluates not, then it evaluates and then it evaluates or. So for example, this here is true because 1 equals 0 is false and 2 equals 1 is false, so this and is false. But then 1 equals 1 is true, and so this becomes true because the or is evaluated last. However, if we put parentheses like this, then this becomes true because 1 equals 1 is true and 1 equals 0 is false, and with the or this expression is true. But now when we do the conjunction with 2 equals 1, the whole thing becomes false. So remember the ordering of the priorities, and also if you have complex expressions, use parentheses to make sure it's doing what you want it to do. You can also test if some element belongs in an array. So you have this in operator. For example, in this case, 12 in 1 to 3, this is false because there is no 12 in that list, but 2 in 1 to 3 is true because there is at least 1, 2 in that list. This also works for substrings inside larger strings. For example, there is an AB there, so AB in X, ABX is true. You don't, in the case of strings, it doesn't have to be just one element. And you can also, since this returns a true or false, a Boolean value, you can also apply not, for example, and so on. But in the particular case of not, there is this syntactic sugar, so to speak. So to get things a bit prettier, instead of having to write not 12 in 1 to 3, which is not very intuitive, it works. Python can work with that, but this is not very easy to read, and this is a lot more intuitive. So 12 not in 1 to 3. This is easier to understand, and Python allows us to write like this. So you can put the not together with the in operator and do the negation of the in operator. The is operator, this one, can compare if variables refer to the same object. This is slightly stronger than equal. For example, in this case, A is pointing to this list 1 to 3, and B is pointing to another list 1 to 3. So if we ask if A is equal to B, it's true because comparing element by element, these lists are equal. However, A is B is false because A is pointing to one object and B is pointing to a different object. So they are not the same object. The lists have the same contents, but they are not the same list. However, C is pointing to the same object as B. So B is C is true. This is one way you can distinguish what happens if you change one of the lists. For example, if you append something, if you do, for example, B dot append 4 or 5, something like this. This would add to this list here, and so it would affect both B and C because they are both pointing to the same list, but it would not affect A because A is not the same as B. So this is another operator that you can use if you want to test if two variables are pointing to the same object. Okay, so let's see how we can use these kinds of expressions, comparisons, and so on to branch our code. We can use it in this statement, the if statement, and I'm going to show you as motivation solving the quadratic equation. Last week we did this approximately by just using the positive root here because we wanted to compute the pH, and so we did not actually solve the quadratic equation, just assumed it had at least one real solution and we took the largest one. But what we need to do to actually solve this equation is to compute first this discriminant here, so this part inside the square root, because this delta b squared minus 4ac will tell us if we have real solutions or not. So if this part is negative, if delta is below 0, then there is no real solution to the equation. If delta is greater than 0, then we have two real solutions, because it's minus b plus the square root of this expression and minus b minus the expression. Otherwise, if delta is exactly 0, then we only have one solution, which is minus b over 2a, because that part there will be 0. So basically we have three different possibilities, and we'll need to branch our execution into the three different branches depending on the value of delta. So to do that, we're going to use the if statement. The simplest version of the if statement only has if, a condition, and then an indented block of code. For example, if a greater than 5, print large. This means that the block of code that is indented inside the if statement, so this could have several lines, in this case it's just a simple one-line block of code, but has this indentation here to show it belongs to the if. This line will be executed only if the condition is true. So if we set a equals 12 and do if a larger than 5, print large, then we can see large here because this line was executed and it printed the string large. But if a is 4 and we do exactly the same thing, now we don't see anything printed because this line was not executed. So this is the simplest version of if. It only tells you whether or not to execute a block of code. For the purposes of if, false is something that's either actually false in the Boolean value false, if it's none, 0, or empty. So all of these four count as false. For example, an empty string counts as false. So if empty string print true, it will not print anything. If the string is not empty, no matter what it has, it counts as true. So if some string print true, it counts as true. The same thing for numbers. If you have 1, it counts as true, but if you have 0, it counts as false. So anything other than 0 counts as true, 0 counts as false for numbers, and for lists and so on. So if you have an empty list, it counts as false, so this is not printed. But if the list is not empty, even if it has a 0 there, but it's not an empty list, then it counts as true. So false for the if statement is false, the actual object false, none, 0, or empty. All of these can be used, can be considered false in the if statement. Everything else is true. Usually I recommend that you use expressions that are evaluated to actually false and true, because that makes the code a lot easier to read. But sometimes you can find examples of if statements to test if something is none or if it's 0 or something like that, and they can just shortcut in this way. One other way of constructing an if statement is to have two alternate branches, but guaranteeing that at least one of them, that exactly one of them will be executed. So to do this, we have if, a condition, one block of code, then else, and another block of code. And what this means is that if the condition is considered true, if the expression here evaluates as true, then the first block of code is executed. If not, then the second block of code is executed. So exactly one of these will be executed depending on the value of the expression. If we have x equal 10 in this case, then it's larger than 5, so it's going to print x is large. If x is 2, it's not larger than 5, so it's going to print x is small. But one of these branches will be executed, and only one of the branches will be executed, because once execution enters one of the branch, it will ignore the other. The general case is to have the if any number of elif. Elif is a contraction of else if, and then the else optionally. So all of these are optional. You can do an if statement with just if, and you can have a large number of elif if you want. So what this does is it checks the first condition for if. If it's false, it checks the elif following that. If the condition is false, it checks the other elif if you have more. If all of them are false and you have an else, it executes the code on the else branch. But once the execution enters one branch, it will ignore all the others. So only one of the branches will be executed. If you have an else block, an else branch here, at least one branch will be executed, because the else branch, even if all the others fail, will be the one executed. If you only have elif branches, it may happen that none will be executed if none of the conditions are met. So this is what we can use to implement the solution to the quadratic equation. We compute delta first, so this is b squared minus 4ac, and now we check if this expression that is inside the square root is negative. If it's negative, then we don't have real solutions to this equation, and we return an empty string. There is an empty list. There are no solutions for the equation, at least in the values of the real set. Else if, this means that if this condition fails, then we're going to test this other condition, delta greater than 0. So if delta is negative, we have no solutions. If delta is greater than 0, then we have two solutions. So we create a list with this expression here. This is minus b minus the square root of delta divided by 2a, and this expression here, which is minus b plus the square root of delta divided by 2a. So these are the two real solutions we have for the quadratic equation. If both of these conditions fail, that is, if delta is neither less than 0 nor greater than 0, then it must be exactly 0. And in that case, we only have one solution, and that is minus b divided by 2a. So this is the branch that determines what is the solution to the equation, and then we return the solution. Okay, now we can test our equation, our function. We're going to solve this quadratic function, and then we have the solution for our test, which is 0.5 and 1, and we can actually write down the quadratic function with these coefficients. So 2 multiplied by x squared minus 3 multiplied by x and plus 1, and we check that if we use x equal to the first solution, we get 0, and if we use x equal to the second solution, we get 0. So this is one way of testing if we actually found the roots for that equation. When you are using conditions, it's important to find tests that cover all branches. So in this case, we are testing one quadratic curve that has no real roots, another one that has two different real roots, and another one that has one double root. So it's only one root here. This is important because if we don't test the three branches, there could be an error in one of them, and our test will not catch it because it will never, execution would never enter into that branch. So remember, if you are implementing functions with conditions, try to test the different possible branches on your code. And we can also create in our module, we can put all our tests in a test function like we did the other time, so that when we run our module, the tests do not run unless we specifically want to run the tests, and in that case we execute the test function. Okay, so now let's see this part of namespaces and scope. We saw a bit of this when looking at functions, but now we're going to expand this a bit more to understand how Python works with the scope of the different names and how we can import objects into our modules. So a namespace, you can think of that as a sort of dictionary where Python is storing the correspondence between different names and the corresponding objects. So that table I showed schematically in the lecture on functions. So if we create a function, a string s equals abcd, for example, then we have this namespace, this dictionary, where the entry s was added and where s is pointing to this string object in memory. But we can have different namespaces because in different contexts the names can be defined or not. For example, the split function does not exist. If you try to split by the comma, we get an error because split is not defined. So in this namespace that we are looking at here, Python does not have a definition for split. But within the string, it does. There is a split method in this string object, and we can use that split method inside the string object. Note that we could also have a split function outside, but they would be in different namespaces, so they would not interfere. And this is an important attribute of namespaces, that you can have the same name in different contexts and have no problem or interference between them, because in different contexts they mean different things, and Python can keep track of all those things. There is one important namespace, which is this built-in namespace, which is where Python stores all the basic names. So the things like int, print, if, things like that, they are all in the built-in namespace because they are part of the language. Now, the scope of a name is the context where the interpreter can understand that name. For example, we saw the local scope for variables inside functions. In this function we have here, we create this var2 variable, and this var2 variable has a local scope. It's only accessible inside this function locally. So if we try to access it from outside the function, we'll get an error because we cannot access that variable from outside the function. The Python interpreter looks at the different scopes in order when it's going to try to find what the name means. It's going to look first in the local scope, then enclosed. We have not seen yet what the enclosed scope is, but I'm going to talk about that in a few lectures. We've seen what the global scope is. It's in the same module, and the built-in scope, it's the last one. It's where there are the reserved names for Python. So when Python is executing this function, we call the function here, we define the function here, we call it here. So execution enters the function and it finds this print statement. There is no variable inside the function called print, so it's going to look outside the function here in the console where we are working in our session. There is no variable called print here in the global scope, but there is a name called print in the built-in scope. So it's going to use that one and it's going to print the value of this variable. Now var1 also does not exist in the local scope. There is no var1 here, but when it looks in the global scope, it finds this variable here. So from inside the function, by looking in order on the different scopes, the interpreter can find variable var1, and so it prints its value, which is this I am global. It prints here when it executes this statement. Then it defines a variable var2, and when we tell it to print var2, it's going to look in the local scope first. This is the first one to look for, and it's going to find var2, and so it prints this one. So this is how things work in practice when we are isolating variables inside the function. Even if we create a variable var2 here, for example, if we call the function, when the Python interpreter reaches this stage, there is a variable also called var2 in the local scope. So in this namespace that belongs to the function. Since this is the first one Python will look for, it's going to find this variable, but it's not going to find this one here. So these will be two different variables existing in two different namespaces. This one can be used from outside the function, but this one can only be seen inside the function. And since this one exists inside the function will no longer see this variable outside. This variable var1, the function can see it outside because there is no variable here. So this may seem a bit confusing, but if you practice a bit thinking about the way Python is going to look for the variable names and what the names mean, then it's easy to understand, for example, why we can print the value of var2 when we call the function, but we cannot get the value of var2 once the function terminated, because from outside the function we have no access to that variable in the local namespace of the function. Okay, so what does this mean when we want to use code in one module that has been written in another one? So in this case, we're only seeing how Python can find either something that is local to the function or global to this session, or if all else fails, it finds it in the built-in dictionary of the basic language keywords and terms and functions and so on. But if we have something in a different module, for example, we created this quadratic, solve quadratic function, and let's say we saved it in this file here, quadratic.py. This is a module, a Python module. So a Python module is a file with the Python source code, and it's called quadratic. If we want to use the function inside this module, without actually opening the module and running it on Spider and so on, we need to tell the interpreter to bring that module or something inside that module into our namespace. And this is what we do with the import keyword. So this import statement, in this case, it's telling the interpreter to import this module as an object into our space here, into our session, into our module, something like that. So wherever you put the import, it will be imported there. This means that now we have an object called quadratic here that has everything the module has inside its own namespace. For example, if we want to use the solve quadratic function, we can say that inside quadratic, I want to use the solve quadratic function, give it these arguments, and it will give me the result. This means we have imported the whole module as an object, and now we can access things inside the module, but these objects that belong to the module are accessible only inside the namespace of the module. So we need to have that dot there and say solve quadratic. If we try to just run the function, this will be an error because it's just the same as with split. There is no solve quadratic out here. It's only inside the quadratic module. But we can import things differently. For example, suppose that from the quadratic module, we only want this function. So we don't need to import the whole module. We just want to use the function. If you use this from the module, import the object, we can import this name directly into our own namespace. And so now we can use it as if it was defined, if it had been defined in the namespace we are currently importing into. We can also import names with nicknames, with some alias. For example, suppose we want to use several things in the quadratic module, but we don't want to keep writing quadratic all the time because it's lots of text and it makes things confusing. So we can just keep with this nickname, for example, QD. So now we can say qd.solveQuadratic, and it's the solve quadratic function from the quadratic module. We just changed the name in this way. This is also useful if you happen to have some specific name in your own code, and by bad luck, whatever you want to import has the same name. So you can use the as to give it an alias and give it a different name in your namespace. It will point to the same object, but it will be a different name. Okay, so let's see an example. Let's return to this example from last week where we wanted to compute the pH of this weak acid solution. But last week we had to cheat quite a bit. We did not actually solve the quadratic equation. We just went for the positive root with the simplified function. Now we don't need to do that because we have a function we can use to solve the quadratic equation. And then we also used an approximation for the logarithm, which is a bit messy and not very good. We also don't need to do that because there is this NumPy library that you have installed if you install the Anaconda that has a log10 function, which is the base 10 logarithm of a number. So we don't need to implement this or do approximations or whatever. We just need to import the function and use it in our code. So this is how our new CalcPH module would look like. We can add documentation for the module. So the same thing we do with functions here, this documentation string that is in the beginning of the body of the function, we can add a doc string to the beginning of the module. It has the same purpose of helping the user understand how the module works. Then it is conventional in Python that we do all the imports at the beginning of the module. Strictly speaking, we only need to do the import immediately before using whatever we are importing. But if we do all the imports at the beginning, it's easy to see the dependencies, what this module depends on existing so it can work. So here from the NumPy library, we are going to import the base 10 logarithm function. And from the quadratic module, the one we created a while ago, we're going to import the solve quadratic function. So now we only need to write the function to compute the pH from the acidity constant and the initial concentration. And we're going to first get the list with the solutions of this quadratic equation. So these are the roots of the quadratic curve. The concentration of hydrogen ion will be the maximum of the roots, because this will give us a positive and a negative solution. We don't want a negative one, but we can use max, which is part of basic Python operations and functions, and just returns the maximum value of an array. So since roots is a list, this will return the maximum value in the list, and this is the concentration of hydrogen ion. And now we return the negative of the base 10 logarithm, which is the pH, the negative of the base 10 logarithm of the concentration of H. So you see, our function now became very simple, and in fact all our code became very simple because most of the things that we need we are just importing from other libraries and reusing them. The documentation for the modules is useful because it also works with help. So help can give you the documentation of functions or also of modules. If you import, let's say that we saved all this code in a file called phcalc.py. So this means that in our folder we have a file named phcalc.py, which is a module named phcalc. So if we import that module, we now have all this file in this object. And if we ask for help on this module, it will tell us this is a module, the name of the module, the description, which is what we wrote here, and it also gives us what functions it has and so on. So it's useful to add doc strings to the module, not only for when you're looking at the code, because it helps understand what the module does and how to use it, but also because you can use help and you can include examples and so on in the doc strings. Remember that in general, Python modules that you install from libraries also have this documentation. So if you are in doubt about something, it's always a good idea to import a module and call help on it to see what it does and how you can use it and examples and so on. Okay, so when you import a module, any module in Python, or even if you just import a single object from the module, Python needs to execute the whole module. The reason for this is that even if we are only importing, for example, the base 10 logarithm or the solve quadratic function, it could be that these functions need to use other functions in the module or even other modules. So Python needs first to execute everything and have all these objects created in memory so that we have guarantees that things will work. So remember that whenever you import a module, Python will run the whole module. This means that if you have some unnecessary code, for example, if every time you run your module some tests are run or some result is output or something like that, this will also happen when you import the module. So this is one of the reasons to put all the test code. For example, here we put all the test code in this function. So that when we import this module, this function is created, but it's not necessarily executed. Unless we actually tell the interpreter to execute the function, the tests themselves will not be run. This means that we can easily import the module here without worrying about what happens when we import the solve quadratic function. So it will just give us the function and not write lots of things on the console or do strange things when we import. Okay, so let's see an example. Oh, by the way, one more detail. If you import a module like this one, NumPy, for example, you don't need it in your working folder because it's installed in your Python installation and the interpreter knows where to find this module. However, if you are using your own modules, for example, this quadratic one, the interpreter needs to find it. The simplest solution for now, we can talk a bit more about some details on this, but for later. But for now, the simplest solution is to just have all your modules in the same folder. So the modules that you write, you can keep in the same folder. The modules that you are importing from standard libraries, they are installed and the interpreter knows where they are. Okay, so let's see an example of using this to retrieve remote data. And we're going to count how many Nobel Prize winners we have per country for a specific category. For example, this case, it's in chemistry, and we have the Wikipedia webpage has this table where you have the photograph of the Nobel Prize winner, the name, the country, and some descriptions and so on. And you have this table in the webpage. So first things we need to do usually if you want to process some remote data is to take a look at the format of the data. Later on, we're going to see some libraries that help us parse HTML files. But for this purpose, I also wanted to show that HTML page is just plain text, but it has all of these notations to indicate, for example, that this is a table row starts here, this is a table heading, these are table cells, and so forth. So basically, it's a text file, but the browser will interpret these different notations differently in order to represent the web page in the way that we see it. So with different styles, the fonts, and so forth. So what we need to know is to figure out where we can find the country. And we have these cells that start with this flag icon class and then include the image and so on and the name of the country here. So if we look for these cells in the table, these are the cells here that have the flag and the name of the country. And so we can just extract these specific cells from the table and list all the countries that have Nobel Prize winners. So basically, we're going to find the cells on the table, which are between the TD and the /TD tags. These are the HTML tags. So the TD one starts a cell and then /TD to end the cell. And this would be the content of this one cell. The country cell has a specific class because of the way it's represented in the table. So these classes are used for cascading style sheets and so on to determine how to represent these elements. But we know that the country cell always starts like this and then has different things, has an image, then a link, and so on. And if we count the number of this greater than signs here on these several tags, we know that the country comes after the fourth one and ends with a smaller than sign here afterwards. So if we can extract this part, we just need to split using these characters and then split again there and retrieve what's between. Okay. So this is just a simple way of parsing HTML because we only want the names of the countries and we don't need to use other libraries for this. So what we need to do is to get the source code for the HTML page from Wikipedia, extract all countries, and then look at which are the unique countries, because some countries will appear repeatedly, and we can sort the unique countries in alphabetical order, and then we're going to count how many times each of these unique countries appears in the complete list. So this tells us how many times each country won a Nobel Prize. And then finally we can just print everything out. So to use HTTP, this protocol, the Hypertext Transfer Protocol, what we use to navigate the web, to use this in Python, it's simple because you have this library called requests that has this function get, which this function receives a URL, so the link, the address for the page you want. And then if everything goes well, you have this text attribute that has the complete source code of the page as a string. So all we need is to import the requests library, get the data from the URL, and then we have everything in a string. Then we just parse the string. This response object, this R here, aside from the text attribute, which has the source code as a string, also has other useful attributes. For example, OK is a true or false attribute. It's true if everything went well. If there is some error getting the data, it will be false. And you can get the HTTP status code from the status code attribute. For example, 200 is OK, is when everything goes well. 404 is when the page was not found. Then you have, I think, 503 if the server was busy, and so on. So you can check this code if something went wrong to see what's happening with your connection. But if everything goes well, then you just need to look at the text and you have the source code for your page. So let's extract the countries from the web page. Let's assume that in this function we are already receiving the text for the web page. So the text, we can get it like this, and we receive the string with the source code for the web page. And now we're going to split our page in where we find this string: table, class, wiki, table, sort table, which is this the start of the table. So I'm omitting here quite a bit of page before the table starts, because then you have a description of the Nobel Prize and so on. But if we do this, we break with this split, we break our string into two parts, the part before the table and the part after the table starts. And when we take the second part, we just get the string starting from the table. So basically we are throwing away everything that comes before the table so we can process the table. Now we're going to split it at the end of the table. For example, here, after the table ends, we have this /table tag. We're going to break there and take the first part. So this is just to give you an example how we can narrow down into just the part that we want. So we threw away everything that came before the beginning of the table by keeping the second part of the split. And now we throw away everything that comes after the end of this first table by keeping only the first part before as a result of the split. Now we're going to split the table in the cell beginning, so all these TD tags, and we're going to see for each cell if it starts with the span, class, flag icon, so that that indication that we have here that this is the cell with the flag and the country. If it starts with that string, we're going to split it according to the larger than sign. So we're going to break it down using these characters here, all of these, and we're going to take the fourth piece, which is this one, and also cut here on the lesser than sign, so we retain only the name of the country. So if you want, you can experiment a bit with this with strings, but this is an easy trick to do. You split and retain one of the strings, and then you split again to throw away another part. So in this case, we are splitting it in this sign to get the string that follows the fourth sign here, and then we are splitting again to retain the first part, and we get the text that is between these two characters. So this allows us to extract the country there. Okay, so now we test this. We use requests, we get the chemistry Nobel Prize winners. Note that this is a large URL, so I'm omitting a part here, but you can check the Wikipedia table or Wikipedia site, or you can check the lecture notes, but just don't copy from the slides because it doesn't fit in the slide and I cut a bit there. So now we send the text attribute of our response objects, which has the whole source code of the page. We send this to the all countries function, and it returns a list. It's going to do this for all the cells, and every time it encounters a country, it appends the country to the countries list. So this is the list of the countries of all prize winners, with some countries repeated because some countries had several Nobel Prizes. So now we're going to extract from here only the different countries, and we're going to sort them alphabetically. This is easy to do. We start with an empty string, with an empty list of where we're going to put the strings, and then for each country we're going to check if the country is not already in the list. If it's not in the list, we're going to append it. However, if this is false, so if the country is in the list, this statement is not executed and the iteration will go through to the next country. So each country is only placed in the unique list the first time it is found. And the second time it is found, since it's already in the list, it is not appended to the list. Okay, so at the end of this block of code, we have all the countries appearing in the unique list only once. And now we call sort on the unique list. So sort sorts the elements of the list in ascending order, and since they are all strings, they're going to be sorted alphabetically. So the result is like this. It starts with Argentina, ends with Yugoslavia, and we only have one country. So each country only appears once on the list. Okay, so this is the other function where you get the list of the unique countries, and now we need to count how many times they appear. So let's generalize this. Instead of just doing it for countries, we're going to do this in general. So we have a set of values and a set of categories, and we want to know how many times each value occurs. So each value is one of the categories, and we want to know for each category how many times it occurs in the values. So we're going to start with a list of counters that they all start at 0. So we need as many counters as categories that we have. And we can do this easily by multiplying a list with only 1 0 by the length of the categories. Because if you multiply a list by an integer, you get a repetition of that list, that number of times. So if there are 10 categories here, we'll get a list with 10 zeros. And now for each of the values, we're going to see which category it belongs to, and we're going to increase the corresponding counter. So to check which category it belongs to, we can use the index method in the categories list to see where in that list what is the position of that value, and then we increase the corresponding counter. So this would be the counter for Argentina, right? The next one for Australia, and so forth. So from here, with the full list of countries and the list of names ordered alphabetically, so this one we got here, we can obtain the count for all the countries. So now we can write the final function that brings everything together, which from the URL of the Wikipedia page, it gets the source code of the page, if there is something wrong, so if it's not okay, the response, it will exit the function with this error. So this is something that you can do. You can check if everything went okay. If your internet is down or something like that, then it will just return error getting data and will not give you the result. Note that this return is only executed if this condition is true, that is, if it's not okay. But once the return is executed, then Python immediately exits the function. So in this case, nothing else will be done if the return is executed. Not because of the if is not to blame for that, but because the return forces Python to exit from the function. So if everything goes well, we get all the countries from the text of the web page. Then we get the different countries sorted alphabetically. We count how many times each country occurs in the names of the different countries. And now we return a table. So basically we start with an empty string, and for each of our names we increment our string by putting the name and a tab, and then the count the number of times we counted the country converted to a string so we can add it to the name, and then this special character for changing the line. So basically there are two special characters here, the tab separator that allows you to do this, to create a sort of table by lining things up, and the new line character that changes the line. So if we did not have this new line character, everything would become glued together one after the other, and you wouldn't see anything in the table format. So these are two special characters that are useful if you want to format strings and show things a bit with some text structure. And now we return this table as a string. Note that I did not write inside the function a call to print the table. In this case, it would not be bad because we are going to print it anyway, but it makes the function less useful because then you cannot use it without printing anything. So it's always best to separate the actual logic of your code, what computes the results, from anything that has to do with interface and showing things and so on. You can create an additional function just for printing or do something like that, but try to avoid mixing the things together because it makes your functions less useful in the general case. So this is what happens when we do chemistry. So I put in the URL for the Nobel Prize winners in chemistry and we get this result. But since the Wikipedia pages for the Nobel Prize winners all have the same structure, our function works equally well in other categories. So we can just put in the URL for physics. We have the list of times each country won a Nobel Prize in physics. We can do the same thing for medicine. Portugal has one in this case. Then for literature and so on. So basically, since the page structure is the same and we wrote our code in a way to use just that structure, in a way that is more generic, we can now use the same code for any page with this structure for the Nobel Prize winners. So to sum up this part, we saw these Boolean expressions, the true and false, and the comparisons, and how we can use the if statement for conditional execution. So when we need to branch our execution. We also saw how we can import objects from other modules. And this will be a very important thing in Python because we have code written for lots of different things, and we're now going to start using code from the standard libraries that you have installed in Anaconda, or eventually you can break down more complex programs into smaller subsets of functions into different modules, and then organize things better by importing from different modules. And we saw this example using the requests library. So for this part, I recommend that you read the chapter 5 of Thinking Python, so from the beginning to through section 5.7. And also, optionally, you can look at chapter 10 for Learning Python, but this book is a lot more detailed than what we cover here, so it's a more serious programming book, and so this is optional you can just take a look at more details there. You also have online the documentation for the requests module. So if you're interested in using online resources in your work, it would be a good idea to just take a look there. Okay, let's take a short break. We'll continue at 6 at 1800 with the second part.